Hello everyone. Today we're going to be looking at limits of functions. Specifically, we're going to be actually doing some calculation of limits for polynomials and ratios of polynomials or rational functions. Now, if you watched part 1, we talked about the concept of a limit. Today is more about how we calculate those limits. Specifically for polynomials, things like this, which turn out to be really easy, often, to calculate the limits. And here I'm going to be making use of some results. I'm not going to prove these results, but we're going to need them. For example, the limit as x approaches a number c of x to any power, any integer power n, equals c to the n. The limit as x approaches c of a number a times x to the n is equal to a times c to the n. Finally, limit as x approaches c of one function plus or minus any other function, I'll put this in big parentheses, equals the limit of the first function plus or minus the limit of the second function, assuming that these two limits exist. Once again, I'm not proving these, but the fact that these things work makes life really easy when we want to calculate the limit of any polynomial like this. Basically, these say that, okay, if I can plug in a number, namely this number 2, which is where we want to take the limit, if I can plug that number into my polynomial, that is the limit. So let's do it for this one. It's a nice, easy example. This limit equals 4 times 2 squared minus 6 times 2 plus 5. That's it. I've gotten rid of this limit sign because we've actually now calculated it. Let's do the little bit of arithmetic we need to do to figure this out. So this is 4 times 4, which is 16, minus 6 times 2, 12, plus 5. 4 plus 5 is 9. So my answer is the limit of this polynomial function as x approaches 2 is in fact 9. Wow, that was easy, wasn't it? You might be thinking, why did we do all that stuff if you watched part 1 of this video series? Why did we do all that when I can just plug in? And once again, we're going to see that a limit isn't about getting to this number. It's about what the value of the function is approaching as we approach this number. Okay, let's try another example. Here we have a rational function. That's basically just a ratio of one polynomial to another polynomial. The same rules are going to apply here. If I can plug in this number into my polynomial, a mathematician would say, if this number is in the domain of this polynomial, then the limit is the value of this polynomial at this number. Wow, that makes it so easy for us. Here we go. I simply plug in 1. 1 squared plus 2 over 1 minus 4. 3 over minus 3. And that gives me my final answer, minus 1. Once again, I've replaced a limit problem with basically plugging in a number into a polynomial. This only works because 1 happens to be in the domain of this polynomial. So of course it makes sense that we need to look at something a little more complicated where this number is not in the domain of the function that we want to take the limit of. Here we go. Okay, this is a great example, right? We want the limit as x approaches 1 of this rational function. Now, notice that when I plug in 1 into the denominator, I'm going to get 0. You may have heard, okay, that's a bad thing. Well, Is math really bad? It's never really bad. But in this case, that leads to a problem, right? 0 in the denominator. You might think, well, okay, some of you might be thinking that's infinity, but you notice that the top of the fraction is also 0 when I plug in 1, which means I get 0 over 0. 0 over 0 could be anything. It could be 1, sure. It could be infinity. It could be any other number. It's what we call indeterminate. So that's a problem. But remember that the limit concept is not what this function is when x equals 1. It's what the function value, the y value, is approaching as x approaches 1, but not equal to 1. Now, if x is not equal to 1, I can do something with this. I can say, okay, this is the limit as x approaches 1. Let's factor the top. And this is a classic technique to doing many of these problems, factoring. So this is the difference of two squares. This factors into this. I still have x minus 1 on the bottom. And this is where the fact that we're not setting x equals to 1, that becomes important because these two terms, they're not 0, which means I can go right ahead and just cancel them. They're gone. It's not 0 over 0 because x is not actually equal to 1. It might be super close to 1, but it's not equal to 1. These are going to cancel. And look what happens. My limit becomes the limit of x plus 1. We've replaced this rational function with a nice simple polynomial. Now, I can actually plug this number in because this number is in the domain of this polynomial, and I get my answer, 2. This limit, even though I couldn't plug in 1 into my original function, the limit still actually exists, and that limit is 2. You may have been wondering, why is this graph here? You may actually recognize a graph like this if you watched the first part of this video series. This graph is this polynomial. If x is not equal to 1, it's equivalent to the line y equals x plus 1. That's this. Notice how there's a hole here. When x equals 1, there's a little open circle. That means that this function is not defined when x equals 1. But the limit is still 2 from our arguments that we were making in our first video. Right? Walking along this curve, what are my y values getting close to? They're getting close to 2. Same thing if I come from this direction. It doesn't matter that the function isn't defined at 1 because we're only approaching 1. We're not going to actually get to 1. So this is a good example of where factoring can help you determine the limit of a function when you can't plug in the number into the function. Let's try another one. Once again, we have a limit of a rational function, polynomial over a polynomial. Now in this case, we have trouble. There's no way we can factor this. 1, we can't plug in 0 because the denominator becomes 0. In this case, we don't get 0 over 0. We actually get a number over 0. And what we would say here is that this limit isn't getting closer and closer to a number. This function is not getting close to a nice number as x approaches 0. And to see this more clearly, let's look at the graph. Here we go. Here's the graph of this function. As x gets close to 0, imagine you're walking along this curve. You're looking at your y values. You're going, okay, are my y values getting close to a number? No, they actually keep getting bigger and bigger and bigger. And it doesn't matter whether I'm going along this part of the curve or whether I'm going along this part of the curve. We say that the y values are unbounded. And in this case, the only answer is that this limit does not exist or is undefined. There's a lot of different ways you can say it. One of those two things is generally acceptable. Sometimes a limit of a function, like this one, depending on the value you have here, it might not actually exist. Limits have to be numbers, and infinity is not a number. Okay, let's do one more problem where we have to use another technique that we haven't learned before. Here I have, it's a rational function. This up here is not a polynomial, right? So this is kind of a new thing, but as usual, we try our best and we say, well, let's try plugging in this number. Can I do it? No, I get 0 in the denominator. I do get 0 in the numerator as well, so I'm thinking this limit may actually exist, unlike the previous example. So the general technique for a problem like this is we multiply by the conjugate of the numerator. What is the conjugate? It is the same thing with a plus sign instead of a minus sign. Now I can't just multiply this by any random thing, but I can multiply by 1. So as long as I multiply by something which is equal to 1, I haven't changed the original value of my function. And you might be thinking, wow, this looks even worse. But stick with me here, it's actually going to be better. Remember that these problems, at an introductory level, these problems are designed so that they work out. Now, if you go further in math, you might begin to discover that things are kind of the opposite of that. But for now, these problems are actually going to work out. So be confident, stick with it. Here we go. Let's multiply the numerators here. And we did this. Why did we do this? You should be thinking, oh, wait, this is x minus y, x plus y. That's equal to x squared minus y squared, where x is 6 and y is this square root. So what do I get? I get 36 minus 36 plus h. This whole thing is y, so put that in parentheses because we're going to distribute the minus sign. Divided by, and admittedly, our denominator here looks terrible for right now, but let's just stick with it. Okay, what do I get? Look what happens in the numerator. 36 cancels. I get a minus h, but that minus h is going to cancel this h. Right, 36 minus 36, that's 0, minus h. So I get minus h on the top. That's going to cancel the h on the bottom. So I get minus 1 over this. 6 plus the square root of 36 plus h. Why is that good? That's good because I can plug in 0 now. Like that line with the hole on the inside. I can plug this number in. We got rid of the problematic factor, which was this h in the denominator. We're almost done. Plug in 0, I get minus 1 over 6 plus 6, and I get minus 1/12. That's it. We found the limit of this function as h approaches 0 is actually equal to minus 1/12. I hope that helps you with your calculations of limits, and I'll see you next time.